Okay, should I go ahead and start?
Uh, Yeah,
Okay,
so I can introduce you. Sorry. Yeah, so today we have Matt Reece from Harvard University, who will tell us about Instanton number asymmetry. Yeah, so please go ahead.
okay, great. Thank you. Thank you for the invitation to talk here. It's good to get an opportunity to talk online because I have not been able to travel much because of having a young baby. So uh, happy to be able to talk to you all. Um, so this talk is kind of based on several different things I've been working on lately, and I want to start by giving you the big picture motivation. So what I want to try to do in this talk is explain to you kind of what my goal is with several of these things I've been working on, and as well as some of the details. The big picture motivation for me is that there's this fairly well established idea that quantum gravity does not have global symmetries. And a thing that I think we've all started to appreciate more in recent years is that gauge theories actually have many global symmetries, many more than people previously were aware of. And in the real world, of course, we have gauge theories and we have gravity. So there's sort of a puzzle. Gauge theories have all these symmetries. Gravity doesn't like symmetries. And the question that's on my mind is, how do we resolve this puzzle? And not only that, but does the resolution have experimentally testable implications? So I'm coming at this from the direction of particle phenomenology and really trying to find something where I can tell my experimentalist friends that there's something worth looking for that's well motivated. So the work I'm going to talk about today is based on three different papers, plus various other some of these threads have been running through other papers I've written recently, and some of it is work in progress. But one of these papers is one that I wrote a few years back called Chern-Weyl global symmetries and how quantum gravity avoids them. Um, Shortly after that, there was another paper about how magnetic monopole loops can generate a mass for axions. And then recently there was a paper on thinking about -1 form symmetries as being spontaneously broken. And so this is with these various collaborators, Ben Heidenreich, Jake McNamara, Miguel Montero, Tom Rodelius, Irene Valenzuela, Gigi Fan, Katie Fraser, John Stout, Daniel Aloni, Eduardo Garcia Valdecasas, and Moto Suzuki. And I want to start by talking about sort of a familiar story, which is thinking about magnetic symmetries and magnetic monopoles. Okay, so in U1 gauge theory, there is uh, there's a topological U1 symmetry whose current is just the field strength. And you integrate that over any closed two cycle, you get 2 pi times an integer. Um, this generates a d-3 form symmetry, which acts on the 't Hooft operators. And the conservation law here is very easy to understand. It's just the Bianchi identity. It's the fact that df is 0. And I've told you that gravity doesn't like such symmetries, so we can ask how can we eliminate that symmetry? And there are sort of two standard ways of eliminating any would-be global symmetry. The first is you can gauge it. In this case, you would gauge it by coupling a d-2 form gauge field to the field strength F. Gauging it has a dramatic effect on the infrared physics. This BF coupling gives the photon a mass, so it decouples it from the IR, and your low energy physics doesn't look the same at all. The other option is that you can break the symmetry explicitly, and you do that by adding dynamical magnetic monopoles, and now we have something on the right-hand side of the Bianchi identity, which is the monopole current. The symmetry itself corresponds to a family of surface operators, which basically just measure the flux through a surface. So these are the e to the I alpha integral of the current. When we gauge the symmetry, we have an equation of motion that tells us that now our current 1 over 2 pi f is equal to the derivative of star h, where h is the field strength of that B field. So the current becomes exact. And as a result, all of these would-be symmetry operators become trivial. So on shell, when we use the equation of motion, this is a total derivative and it integrates to 0. So gauging just kills all of these operators. Breaking, on the other hand, is a different story. The operators still exist, but now the charged operators, the 't Hooft lines, can end on the operators that create magnetic monopoles. And so if I measure the flux up here, uh, I measure something non-trivial, and I say this operator would act by producing a phase. If I measure the flux down here, I've slid it off the end of the line, and there's no flux, and it doesn't do anything. So what that means is these operators are no longer topological. They exist, they're non-trivial operators, but we don't call them symmetries anymore because they're not topological operators.
Hello, Matt. Just a
Yeah.
quick question. So in the
Sure.
first option of gauging it, don't we
Yeah.
generally get another symmetry, another global symmetry from the Bianchi identity of B?
Sure. There are other possible symmetries that arise, but they can also be broken if we add the appropriate charged objects, right? So
Sure, yeah, but I
it's
guess my point
certainly.
is that gauging doesn't completely eliminate.
Oh, I agree. Yeah, sure.
It does the
So
job,
so
right?
so if we
Whereas
gauge the
breaking it,
symmetry, um, well, actually, in this case, sorry, if we actually have a BF theory where I have kinetic terms for everything and a mass, um, I actually don't have any uh symmetries in this case because the strings can end on monopoles.
because
Um,
you work out
so
a function for A who said
yeah,
that,
I think in this case I actually don't have any, but I agree in general with what you're saying. The gauging operation is not necessarily the end of the story. If we're
right,
asking whether there are symmetries, sometimes there are new symmetries that
right,
arise in that case, and we could worry about how those are either gauged or broken. Well, if those are gauged, you usually get back to where you started,
right,
or they
right,
could be
right,
broken.
right. Whereas breaking
So
seems to be more efficient, right? Just break it.
yeah, yeah. Okay, thanks. Um, okay, in at least a lot of examples, there's this sort of interesting distinction between gauging and breaking, where when you gauge a continuous symmetry, it's often very visible in the low energy effective field theory, right? So we're all familiar with gauging ordinary symmetries, and we get propagating gauge fields, photons and gluons and things like that. Um, if we gauge the one form symmetry, as I said, the gauge field gets very heavy and it decouples. Um, Breaking these symmetries is sometimes less visible in EFT, right? So if the symmetry is broken by monopoles and the monopoles are very heavy, if you're a low energy observer, you don't necessarily notice. Um, but it's still true that the monopoles are describable in effective field theory, right? So even if they're very heavy, I can have some sort of world volume effective theory of these objects where I only talk about the low energy modes that interact and I sort of treat the object as a defect. And often the breaking is visible there. And I'll say more about some examples in a little while. But what I like about this particular example of the magnetic monopole is it makes a real world prediction. Because we say we don't believe in global symmetries. U1 gauge theory has a global symmetry. What are our options? The first option is to gauge it, but that doesn't look like the world around us because we see a massless photon in the world around us. Um, so it seems like it really has to be broken, and if it's broken, then magnetic monopoles exist. Okay, so that's a prediction for the real world. It's a prediction that you can hope to test in experiment. It's unfortunately not a very useful prediction for experiment because it doesn't tell you what the monopole mass is. It doesn't tell you how to build a practical experiment that would find it. But I want to highlight that this is sort of a well understood example that follows this strategy. We identify a symmetry, we categorize the different ways you can gauge it or break it, and we try to understand which ones are possible in the real world. And this is the strategy that more generally I am trying to follow and trying to find other examples and hoping that some of them will make contact with things that people can actually measure. Okay, and so the main topic of my talk is going to be instanton number symmetry. So gauge theories have lots of topological symmetries. I just told you about one of them. From the mathematical viewpoint, these are things that would be called characteristic classes associated with gauge bundles. And so one familiar example is the instanton number, which we see in non-abelian gauge theory. And so there's a current trace F wedge F. And let me work in 5 or higher space-time dimensions for the moment, so that this is a non-trivial statement. D of trace F wedge F is equal to 0, and the way that you see that is you see that you can add in these commutator terms by anti-symmetry, and then you get something that involves the covariant derivative of the field strength, and that's 0 by the non-abelian version of the Bianchi identity. Okay, so this is a conserved current. Um, this is not an original statement I'm making. People have talked about this many times in the past. Um, there's a whole lot of these currents in general. We could take, you know, if we're in high enough dimensions, we could take different numbers of Fs and wedge them together. We could do things like, sorry, we could do things like taking different U1 gauge theories and taking F of one, wedge F of a different one. There are many things of this general flavor that you can do. And so a few years ago, my collaborators and I tried to advertise these under the name Chern-Weig global symmetries, just to emphasize to people that these things exist quite generally, and it's interesting to try to ask what quantum gravity does to all of these would-be symmetries that gauge theories have. And I would call these symmetries U1 symmetries because if I normalize things appropriately, there's generally some integer label. So for instance, for SUN gauge theory, 1 over 8 pi squared trace f wedge f integrates to an integer. Of course, if we do different groups like PSUN or SON, we have to worry about the normalization being different, but generally there's some integer label. So let me mention PSUN now. So PSUN is the quotient of SUN mod ZN. And this is an interesting example that has another kind of symmetry, which is a discrete symmetry. There's a Zn valued quantity that's the obstruction to whether you can lift a PSUN gauge bundle to SUN. And this seems to be called a Stiefel-Whitney class by physicists. It's a Zn valued thing. I think maybe mathematicians tend to use Stiefel-Whitney for things that are Z2 valued. I don't know if they have another word for this. But this is some closed form, and it generates a Zn E minus 3 form global symmetry, which is just the analog of the magnetic U1 symmetry for this theory. And you can also do the kind of thing we were doing before. So for U1, I could wedge together different Fs. For SUN, I could do trace F wedge F. Here I can do things like taking products of W2s with itself, and I can generate various lower form symmetries. In general, the basic magnetic symmetry, the D minus 3 form magnetic symmetry, exists anytime you have a non-trivial fundamental group for your gauge group. And the fundamental group labels the symmetry charges, and the symmetry group is the Pontryagin dual. Now, let's start with U1 and talk about the symmetry generated by F wedge F. Okay, so again, the integral of 1 over 8 pi squared F wedge F is an integer. This is some U1 symmetry. But if you have monopoles, which are breaking that symmetry that we already had, then they obviously break the symmetry because I take d of F wedge F, and df is non-zero, and so I get something non-zero here. So that's a very simple argument, but I want to give you a more complicated argument, and then I'll explain to you why I spent your time on the more complicated argument when there's such a simple argument. So the more complicated argument is, if I really have a good symmetry, I should be able to couple it to a background gauge field. Okay, so in this case, that would be some D minus 4 form gauge field that I'm going to call C. So I imagine I have some Lagrangian like this, where I've turned on some kind of background gauge field. And I want to think about how this gauge field interacts with the existence of magnetic monopoles. So I have a U1 gauge theory. For now, let me not turn on. Well, I'm for the moment. Let me assume I'm in more than 4 dimensions, so I don't have to talk about a theta term. We'll come back to theta later. So ordinarily, I can introduce a magnetic gauge field by saying, well, I take the thing that's the electric flux and I make it the magnetic flux of this other gauge field, which I'll call AM. And so this is telling me that star F is D of AM. That only makes sense, locally if D star F is 0, which is true away from sources. But once I've turned on this coupling to this gauge field C, now my equation of motion is different. D star F is not 0 anymore, it's DC wedge F. And what that means is that if I want to introduce a magnetic gauge field, I have to be a little bit more careful. I have this modified Bianchi identity, and I can define my magnetic gauge field by solving this equation. I have a new term over here, which looks like C wedge F. The problem is that this is not gauge invariant anymore, because C is a gauge field, it has a gauge transformation. If I shift C, if I do a gauge transformation, then my solution for the magnetic gauge field is different. Okay, and this is quite general when you have Chern-Simons terms and you want to do magnetic duality. Chern-Simons terms dualize to Stuckelberg terms, where one gauge field shifts when another gauge field transforms. But this has an immediate implication for monopoles, which is that if I try to write my monopole world volume action by integrating this magnetic gauge field over it, this is not a thing I can do when I couple to this background gauge field C. This is no longer a gauge invariant quantity. And so that's one way to argue that symmetry that was generated by F wedge F is broken. I tried to gauge it with C. Trying to do that leads to some clash with the world volume action for magnetic monopoles. Okay, so that is an argument for symmetry breaking, which sounds a lot more complicated than this argument that I just take D of F wedge F and I get something non-zero. So you might ask, why did I go through this cumbersome story? And there are 2 reasons. Sorry.
Can I ask you a question about this? So in 5-dimensional superconformal field theories, we believe that there are magnetic monopoles, and also there is this instanton number symmetry. and they both exist simultaneously. So do you know what the resolution is there, why it's not broken?
Yeah, so I think it's what I'm going to tell you, although I'm not sure that I'm familiar with the specific examples that you're talking about. But yeah, I will tell you how you can have the symmetry after all. That's the next thing I'm going to get to. Okay, so the reason I went through this story, first it generalizes to 4 dimensions. That's actually one of my main reasons for doing this, because the statement that f wedge f is conserved is sort of trivial in 4 dimensions, but there's still actually an interesting story there. The second reason I went through this is it suggests a way that we can still have some version of the symmetry. And that is to suppose that there's more going on the monopole world volume. Right, so I told you the monopole world volume had this effective action that was not gauge invariant, but maybe there's going to be other things there that patch up the gauge invariance. And so suppose I have a scalar that lives on the monopole world volume. It's a compact scalar, and it transforms when I do an A gauge transformation. So when I do a gauge transformation of A, the scalar sigma shifts. So I can build some invariant, some covariant derivative, d sigma plus A, that is invariant under the A gauge transformations. And I'm going to call this a Dion collective coordinate because it turns out to be the thing that gives the monopole electric charge. And so if I have this degree of freedom that behaves in this way, I can build a world volume action. Maybe it has some other terms like a kinetic term for sigma. But the important term for our purposes is I can couple the background gauge field to the covariant derivative of this thing. And so now when I do a gauge transformation of A, when I do a gauge transformation of C, the magnetic gauge field A had this extra shift that was uncompensated before. But now C shifts, and there's another coupling of C to A, which is from this covariant derivative. And so I get a plus d lambda wedge A here, I get a minus d lambda wedge A here, and they cancel. This is essentially the story of anomaly inflow, right? So this is also closely related to the Witten effect. And you can think of the Witten effect and the Dion mode on monopoles as being an example of the general anomaly inflow story. So what I just showed you is that when I do the C gauge transformation, the pieces involving A cancel. There's a piece that doesn't cancel, which is d lambda wedge d sigma. But these are compact scalars that are normalized such that their fluxes have integral periods. And so even though the monopole action is not invariant, e to the I action is invariant, and this is a perfectly well-behaved thing to do. Okay, so we can couple the monopole to a background gauge field if the monopole has a localized degree of freedom on its world volume that transforms in a specific way. Okay. And you could also engineer things with multiple degrees of freedom on the world volume that collectively cancel the anomaly inflow. But when you do this, you do have a valid d-5 form symmetry in your U1 gauge theory. The current is not just f wedge f, it's f wedge f plus a localized term. The monopole current, you think of like a delta function that localizes you to the world volume, and then you have these pieces that involve the localized degrees of freedom there. And now when I take the derivative of this, I have this df piece, which is not 0, but I also have a piece over here, which is not 0, and they cancel. Okay, so Dions can give us good symmetries even when there are monopoles. And I think that must be what's happening in the 5D examples that you were asking about as well. Okay, so to summarize, a magnetic monopole always breaks the symmetry whose current is f wedge f. But if the monopole has a Dion mode, there can be an improved symmetry, and that symmetry can be gauged. Now, it's not the case that every monopole always has a Dion mode. This depends on the UV completion of the theory, and I'll show you some examples later, some that have it and some that don't. But what I want to emphasize is that even though the UV completion is necessary to know whether the mode exists, the mode can be described in an EFT, which is just the world volume EFT, where I don't know what happens in the monopole core, but I just have some effective theory that lives on the world volume, and I talk about how it couples to the bulk fields. Okay, so this is a story that is specific to U1, but in fact, it generalizes to other gauge groups that are not simply connected. And this is something I've been thinking about recently. For example, we could talk about the case of PSUN. PSUN gauge theory has an instanton number, and unlike SUN, it allows fractional instantons. Okay, so the integral of 1/8 pi squared trace f wedge f can now be a multiple of 1/n. For SUN, the instanton number is an integer. Okay, so that tells you that if I have a gauge field configuration with a fractional instanton number, it cannot be lifted to SUN, so it's somehow related to having an obstruction to lifting PSUN to SUN. That obstruction, as I mentioned, is measured by the Stiefel-Whitney class W2. And in fact, there's a nice formula that's well known that tells you basically that the fractional part of the instanton number is something you can compute just in terms of W2. So modulo 1, basically, this integral of trace f wedge f turns into an integral of W2 squared. There are subtleties whether n is odd or even, and I'm going to not talk about those at the moment. And so you can think of the PSUN monopoles as breaking the instanton number symmetry, because the PSUN monopole is something where dW2 is not 0. This Zn d-3 form symmetry is broken by the monopole. And so that means that this kind of composite symmetry is also broken, because now d of this product turns into something like W2 cup the magnetic current. Okay, so basically this is telling you that it's possible to change instanton number by multiples of 1 over n in PSUN gauge theory using the monopoles that broke the Zn d-3 form symmetry. And I think this story is quite general. So I think it's often the case that these instanton number symmetries, when you have a gauge group that has a non-trivial magnetic symmetry, that has a non-trivial fundamental group, these different lower form symmetries that are built out of multiple copies of the field strength can also be broken by that same fundamental object. It's also interesting to investigate whether these monopoles can admit Dion modes that restore symmetries, and I don't have a complete story to tell you about that, but it's something I've been thinking about. I want to go back to the U1 case and talk about an example of a UV completion, which is to start with SU2 gauge theory and Higgs it to U1 with an adjoint VEV. So this is the standard Tuf-Polyakov story where we find a monopole, which is a soliton. In this case, there are W fields that live in SU2 that are non-trivial in the core of the monopole. And when you do a U1 gauge transformation, you rephase them. And so this classical solution has a dionic zero mode, and this is well known. This was found by Jakiev back in the 1970s. And so this is an example of that story where we do have a symmetry, even though there's a monopole. From the IR point of view, the monopole breaks the F wedge F current, where the little f I'm using here for the U1 as opposed to the big F that I was using for SU2. And there's a Dion mode. It has charge 2 in terms of the fundamental U1 charge because it's coming from the W charge, whereas SU2 has things that are half charge. So the story is a little bit different at the factor of 2 level than the one I told you before, but it works out. And you can show that this infrared current that is conserved and involves the Dion is the thing that you get when you match the SU2 instanton number current in the UV. Okay, so UV SU2 instantons match to something non-trivial involving Dions in the IR. Recently, I've been playing with more complicated examples of this story. So for instance, something that might be of interest for particle physics is breaking SU5 to the standard model gauge group SU3 times SU2 times U1 mod Z6. Here, if you're a UV observer, you say, I have an instanton number in SU5, I have a trace F wedge F. And if you're an IR observer, you say, well, I have 3 different things like that. I have trace F wedge F for SU3 and SU2, and I have F wedge F for U1. And so I seem to have more symmetries in the IR than I had in the UV. But the IR theory admits monopoles. And if I embed an SU5, I get such monopoles as solitons. And the minimal monopole is something where you wind 1/6 of the way around U1. You wind you go from the origin to the non-trivial center elements of SU3 times SU2, and then the Z6 quotient takes that non-trivial path in SU3 times SU2 times U1 and wraps it up into a loop. Okay, so there's a minimal monopole, and it has fluxes for all 3 gauge groups, which in some normalization are the things that I have written here. So in fact, that monopole breaks all of these currents. It breaks the trace F wedge F for SU3, for SU2, and for U1. But there is a Dion mode, and you can work out what this Dion mode is, and it has electric charge under SU3, SU2, and U1. So in fact, it shifts under gauge transformations of all 3 of these fields. And what you can show is that this Dion mode actually rescues just one linear combination of the three different IR currents. And it's the one that matched the SU5 and the UV. Okay, so I think this is a quite general story. We have checked this in certain examples, and we're trying to construct a completely general proof. But what I think is true is that anytime you start with a gauge group G and you Higgs to a gauge group H, in the IR you can have more apparent instanton number symmetries than you had in the UV. But the extra ones are all broken, and they're broken by monopoles. And these monopoles admit Dionic modes, which have just the right structure to rescue all of the UV instanton number symmetries. So I think that in that sense, these extra symmetries are sort of accidental, and their UV breaking is visible in the monopole rolled volume effective theory. Okay. So I've been talking about theories in 5 or more dimensions, and now I want to talk about 4 dimensions because I really want to try to connect this to particle phenomenology. Now, in 4 dimensions, you might be skeptical that there's any interesting analog of the story I just told you because this instanton number current is a top form, so it's a trivial statement that DJ is 0. And you might say, well, then this whole notion of symmetry is just vacuous, right? How could you ever break such a symmetry? It's clear, DJ is 0. But I want to argue that there's a way to think about such symmetries that is useful and well-defined, that has a lot of analogies with the higher form U1 symmetries, and that it makes sense for these symmetries to be either gauged or explicitly broken. Okay, so I'm going to talk about what I call a U1 minus 1 form symmetry. I'm not going to worry about what minus 1 form symmetry means in complete generality, but the things I'm interested in are all things where there's some integer charge, and so I'm going to call it a U1 symmetry. And what I think is a productive definition of such a symmetry is this. I'm going to call a top form current a minus 1 form U1 symmetry when I'm allowed to couple it to a background axion, basically a background 0 form gauge field, which is a compact scalar. Okay. And so you should think this doesn't have an analog of sort of small U1 gauge transformations, but it has an analog of kind of large or winding gauge transformations, which is just when I shift theta by multiples of 2 pi. And one argument in favor of this definition that I'm giving you is that if I start with a coupling with a U1 gauge theory for a higher P form and higher dimensions, and I compactify, I can get such a thing where theta is just the integral of that gauge field over the compact dimensions. Now, given such a definition of what I mean by a minus 1 form U1 symmetry, we can gauge it. And the obvious way to gauge it is to say, well, that symmetry allowed us to couple to a background axion. Let's just make that axion dynamical. Sum over it in the path integral. Maybe we'll give it a kinetic term. If I give it a kinetic term, I can derive an equation of motion, which says that my instanton number current is d of the axion shift symmetry current. It's a total derivative. And so instanton number vanishes on shell, and that's the hallmark of having gauged something. Now, interestingly, there's a different way that you can gauge instanton number in 4D theories, which is if I have a chiral fermion, and there's a chiral anomaly, which is unbroken except by, there's a chiral symmetry, which is unbroken except by the chiral anomaly. Then I have an equation of motion that tells me the derivative of my chiral current is this instanton number current. And so once again, the current is a total derivative. And this is basically what happens in the massless upquark solution to the strong CP problem. You have an unbroken chiral symmetry that acts on the upquark. It's anomalous, so it's not really a good symmetry, but it does enforce an equation of motion that tells you that the QCD instanton number becomes 0. And in that sense, it's like the axion in that it's gauging this would be minus 1 form symmetry. Now, recently, with a few collaborators, I wrote a paper that just points out that there are some further analogies that I think are useful, which are thinking about such symmetries as being spontaneously broken. So I claim that the way to think about spontaneous breaking of these minus 1 form global symmetries that I'm telling you about is that the vacuum energy has non-trivial dependence on a constant theta background. The first argument in favor of that is there's sort of like a Goldstone pole. Of course, there's not a Goldstone boson, right? I don't know what it would mean to have a boson that's a minus 1 form boson. That's not a propagating field. It doesn't mean anything. But there's sort of this well-known story that goes back to Kogut and Susskind and to Lucier that you can think of your symmetry current as being a total derivative, and you have this topological susceptibility, which is measuring the vacuum energy's dependence on theta. And if this is a non-zero number, then when you rewrite this in terms of a correlator, a two-point function of the thing whose derivative is your current, that two-point function looks like it has a pole in it. So for example, you can do this in 2D Maxwell theory, 2D QED. You can do this in 4 dimensions with gauge, non-abelian gauge theories, and then this V would be the Chern-Simons current. And so this is a pole in something that's not gauge invariant. It's not a propagating particle. But I would say there's a sense in which you can think of it by analogy to the higher P-form cases as signaling that in the IR there's some kind of emergent D-1 form Goldstone field. This is, in fact, these words, similar words have been said by Gabadadze and Shipman and Diwali, and there's sort of a story about thinking about the strong CP problem in this language. I'm just kind of attaching a different set of slogans to it that I think make certain analogies more clear.
So can I ask a question about the breaking with adding fermions?
Sure.
Yeah, because this is interesting that in this case, effectively you're gauging the symmetry without producing any other symmetry. But it's not directly clear why can you interpret this as gauging. Is there a way to interpret this as the gauging one symmetry and then breaking as
Sorry, the sound was breaking up at the very end there. Is there a way that what?
sorry. In this case, it seems that practically we are gauging symmetry without producing any other symmetry.
Yeah, you're gauging it without producing another symmetry. I think that
Yeah.
is true.
Yeah,
Well, actually, we should worry. There could be non-invertible symmetries potentially to think about in some of these examples.
well, in this non-abelian case, you will not produce any non-invertible symmetry.
Not in SUN at least. Yeah.
Yeah.
Right. So yeah, I think it's true. In some cases we do this without producing new symmetries. But like I said before, I don't think that's completely novel. Just the simple case of gauging the magnetic symmetry of U1 gauge theory, there were no symmetries. I think in general, the statement that you produce a new symmetry when you gauge something, I guess it's true in most or maybe all examples I know that involve discrete symmetries, but I don't think it's necessarily true for continuous symmetries. Okay, so I'll get back to what I was saying before. So another argument for thinking of non-trivial vacuum energy as spontaneous breaking is that when we gauge a spontaneously broken U1 symmetry, we get a gauge theory which is Higgs. And again, there are some nice analogies with what happens when we gauge this theory. If I make the axion dynamical, of course, it acquires a mass from V of theta. That's just directly telling you that axion has a non-trivial potential. And so in that sense, it looks like Higgsing. Higgsing a U1 symmetry is also associated with confinement in the magnetic dual phase, and that again happens here. So the objects that are confined are the magnetically charged objects, which for theta are vortices, right? So like in 4D, these are strings, axion strings. In general, these are codimension 2 objects that theta winds around. And these objects are confined, and the things they are confined by are domain walls. So when you interpolate from 0 to 2 pi in theta, you get a domain wall that sees the energy cost of the potential V of theta. And this domain wall can end on the strings. So we have dual confinement, and closely related to dual confinement is the Stockelberg language, which in this case is that if I dualize theta, I get some object that has a non-trivial kinetic term that also involves this emergent Goldstone field C D-3. Okay, so that Stockelberg language is one place where thinking of this thing as an emergent Goldstone field is a useful thing to do, and slightly different terminology. This was something that Diwali really emphasized some years ago. Okay, so I would claim that there are many reasons why -1 form symmetries seem to have nice analogies with higher form symmetries, even though they're slightly exotic objects in some sense. And another analogy is explicit breaking. Okay, and this is the one that I said you might be suspicious of this because DJ is obviously equal to 0. So you might say clearly I can never break this symmetry. But I claim that there is a sense of explicit breaking, and it's visible in the definition I have given you, which is that we test whether there is a symmetry by seeing whether we can couple to a background axion. And in fact, there can be obstructions to coupling to a background axion. And furthermore, a magnetic monopole can give us such an obstruction. So in that sense, it's very analogous to the U1 case. And the analogy just goes through completely. If you want to dualize to a magnetic gauge field in the presence of this axion, you have to solve this equation. And now when theta shifts by 2 pi, my magnetic gauge field shifts by a multiple of the electric gauge field. And that is exactly the Witten effect that tells me that when I take theta from 0 to 2 pi, I have this monodromy where magnetic monopoles acquire electric charge. So again, just as in the higher dimensional case, I cannot write an effective theory on the monopole world line that just involves the magnetic gauge field because it's not invariant when I do a theta gauge transformation. Okay, so this is an obstruction to coupling to a background theta gauge field. But precisely as in the higher dimensional case, this can be patched up if there is a Dion degree of freedom that shifts under the electric gauge field's gauge transformations, and I can couple that to my axion, and then everything works out. Okay, so it is possible for the -1 form global symmetry of U1 gauge theory to be explicitly broken by monopoles. It is also possible for some improved symmetry that involves localized degrees of freedom on the monopole world line to be unbroken. And this part is maybe a little bit of an aside, but some collaborators and I a few years back realized that this allows for monopoles to generate potentials for axions. So in the language that I was just telling you about, I would say that in theories where I have monopoles and I have a Dion mode, in fact, the -1 form symmetry is spontaneously broken. There's a non-trivial V of theta. And you can see that because I have these Dion modes and their mass spectrum depends on theta. The Witten effect tells me there's some monodromy. So I have states that I have a fundamental monopole. I have cousins of that have integer units of electric charge. And as I vary theta continuously, they sort of transform into each other. And their mass will vary in some continuous way. And kind of the leading order thing you would expect is this kind of quadratic dependence.
So Matt, can I ask a question about the previous? So is the statement that if you didn't have a Dion mode on the monopole, you could not couple an axion to that particular -1
That's
form
right.
symmetry?
Yes. Yes.
Okay.
In that case, the monopole world line action is simply not defined.
And so does this come up in some example?
Yes, I will show examples later.
Okay. Thanks.
Okay. So when we have the Dion degree of freedom, we have a good -1 form symmetry. It's not explicitly broken, but it can be spontaneously broken. And one way to see that is we have these states whose mass depends on theta, and you can integrate them out and sum over all of the different Dion modes, and you find some potential. You can also do a Poisson resummation, reinterpret this sum over the Dion modes as sum over winding. So I think of the monopole as being a loop, and the mode sigma can wind around the world line. In that picture, it's really clear from thinking about the improved current. Let's see, I didn't write the improved current for the U1 case, but I wrote it. Right, so back here, for example, I have an improved current. It has a structure like this. I'm used to thinking about instantons as things that have non-trivial integral of f wedge f, but I could also think of things that have non-trivial integral of d sigma wedge the delta function for the world line. And so that's something that has a non-trivial integral of d sigma, so non-trivial winding. So that is just a Poisson resummed version of this other calculation, and you can do the calculation and you get a nice answer, which is that you get something that looks like it has an instanton action that depends on the monopole mass and on the splitting among the Dion modes. And if you check for the Polyakov case, you just plug in what these things are, you get that this action is 8 pi squared over g squared, just like the SU2 instanton action. Okay, so I would argue that these are the U1 analogs of instantons in non-abelian gauge theory. More specifically, if you start with non-abelian gauge theory and U Higgs, there's some direct matching between these things. But in general, I would expect any axion that interacts with the photon to get a mass, at least from U1 instantons of this form. Figuring out how it depends on fermion masses is more subtle and related to the Kalin-Rybakov effect, and I'm not going to say anything in detail about that now, but I hope to be able to give a talk at some point in the future where I give a clear explanation of that. Okay, so what I've tried to convince you is that many aspects of these -1 form U1 symmetries are very closely parallel to higher P form symmetries. And because of that, I expect that quantum gravity does not like these things either. I can't say that I have a sharp argument involving black holes or holography or anything very rigorous, but just sort of reasoning by analogy, it seems like these things behave very much like things that quantum gravity does not allow. You could think of this as being special cases of the no global symmetries statement about quantum gravity, or of the conjecture that you have no non-trivial cobordisms from McNamara and Vafa, if I'm extending that not just to the space-time manifold, but to gauge bundles. I can't say I have an argument for this, but it's something that I think is probably true, and I would be very happy if someone can put together a nice argument for it. In 4D gauge theory coupled to gravity, if I follow this logic, and I don't believe quantum gravity allows me to have these symmetries, then instanton number symmetry had better be either gauged, which could happen by axions, or again by chiral fermions, although that case is a little bit odd because I have to postulate a chiral symmetry which is broken only by the anomaly, which is certainly not my expectation as an effective field theorist. I think that once the symmetry has an ABJ anomaly, it's not a symmetry, and why don't I write other things that violate it? Or it should be broken explicitly, in which case I expect the theta parameter is not cannot be a general background. It can't take arbitrary values. It's frozen to some discrete set of possible values. And this breaking may depend on very heavy objects that I don't see as a low energy observer, but at least those objects should have some EFT that describes their world volume in terms of low energy degrees of freedom, and the breaking should be visible there. Okay, so these are expectations. Again, these are not rigorous arguments, but these are things that I think are likely to be true. And so I've been trying to follow the logic of if these things are true, how far can I get with trying to understand potential real world implications? And so now I want to go through some examples. I'm going to look at examples in string theory where I have gauge fields, and I just want to ask, is the instanton number symmetry gauged or not? Is there some gauge field that couples to trace f wedge f or not? And I'll show you both kinds of things happening, breaking and gauging. And along the way, I want to keep an eye on these magnetic defects that play a role in symmetry breaking. And I also want to keep an eye on how heavy are the electrically charged states. So let me start with an example from Chakotay and Vafa a few years back. They wrote a paper actually arguing that maybe the strong CP problem is sort of trivially solved in string theory because there's some deep reason why theta just has to be exactly 0 and can't be anything else. And the story they told is about a rigid Calabi-Yau. That means that the only 3 cycles are the holomorphic 3 cycle and an anti-holomorphic one. And the gauge field they were interested in is a U1 gauge field that I get by taking the 4 form in type 2b and integrating over the holomorphic 3 cycle. There's no modulus here. There's no vector multiplet to give me a modulus. And so they argue that the gauge coupling and theta angle are both frozen. And then they argued that assuming some mathematical conjectures, in fact, theta should be 0 or pi. Now, from my point of view, one way to think about the breaking here is there is a magnetic monopole for this U1 gauge theory. It's a D3 brane that breaks, that wraps the anti-holomorphic cycle. You can ask, what are the electrically charged fields here? My gauge field comes from C4, so the charged things are D3 branes, and the electrically charged objects are D3 branes that wrap omega. And so the monopole and the electrically charged particles here are both very heavy. My rough expectation is this 3 cycle volume goes like the square root of the overall internal volume. And so these things live at the Planck scale. Okay, so this is an example where I have a string theory, I have a gauge field, and I have a deep reason why theta is not a continuous parameter. But it doesn't look a lot like the real world because there's nothing light that carries charge. Another example is Kaluza-Klein theory. Start with d-dimensional gravity, compactify on a circle. I get a U1 gauge theory in lower dimensions. And again, there is no gauge field wedge f term in the effective action. There may be other interesting terms, like in string theory examples, I may have a gauge field wedge Kaluza-Klein field strength, wedge winding field strength. There are interesting things to say about that, but the basic question of does F wedge F for Kaluza-Klein get gauged has the answer no, it does not. There's a magnetic monopole here, the Kaluza-Klein monopole, and it has no dionic excitation. This is, again, just a fact about the solution. You look at its zero modes, there is not one associated with giving it electric charge, with giving it a boost around the KK circle. And so the F wedge F symmetry is explicitly broken. In this context, we have electrically charged particles, which are Kaluza-Klein modes. Their mass is 1/r. So they are heavy. I don't see them in the low energy effective theory. And in fact, their mass scale coincides with the core size of the monopole that breaks the symmetry. Okay, here's another example where we see gauging for the first time. In heterotic string theory, we have a gauge group, either spin 32 mod Z2 or E8 times E8, with sort of an outer Z2 that permutes them. In both cases, the instanton number symmetry is gauged. The corresponding gauge field in the 10D theory is B6, the magnetic dual of the B field that the fundamental strings are charged under. And this is just what we learned from Green and Schwartz. There's a modified Bianchi identity for B2, and it means that B6 gauges these instanton number symmetries. But it's worth thinking more about the case of E8 times E8 semi-direct product with Z2. Because here we really have two different instanton number symmetries, one for each E8. And what B6 is gauging is the sum of them. And you can ask, well, what about the other combination, the difference? And there is no gauge field that couples to those. So that one's explicitly broken. But E8 has trivial fundamental groups, so there are no monopoles for E8. So this looks like an example that's different than the other examples. Now, one easy way out is just to say, well, this combination of instanton numbers, the odd combination, is not invariant under Z2. So maybe I don't care about it, right? It's not a gauge invariant symmetry current. And that was my first thought when I thought about this example, but I talked to Jake McNamara about it, and he emphasized to me that that's not a totally satisfying answer, because you could still imagine having a gauge field, which is some B prime, which is a 6-form gauge field, which is odd under Z2, and which is able to couple to this. And so maybe we need a better understanding of exactly what's going on here and exactly how it generalizes to other examples. There is a defect in this theory, which is a Z2 vortex, where when you go around the vortex, you have the Z2 permutation that swaps the E8s. And so maybe you should think that that is the defect whose world volume theory makes the breaking visible. But I would say that this is an example where I feel like I don't yet understand everything that I should be saying about it in the context of a bigger picture story. Another example is gauge fields that live on D-branes. I have gauge fields on the brane world volume. They couple to an RR gauge field in the bulk. When I dimensionally reduce, this becomes an axion. This, in fact, is a story that drives a lot of the string phenomenology literature, where people think about how to get axions out of string theory. There's a thing that might bother you here, which is that, of course, this gauge field doesn't just couple to this current. It also couples simply to D-branes in the bulk theory. And so it's really coupling to a linear combination of these things. And there's a nice story that was understood back in the mid-90s about this, which is that, in fact, so this is gauging one linear combination of currents, and the other linear combination is broken, and it's broken because these are sort of secretly the same object. If I take a Yang-Mills instanton, which is sort of bound to the brane because it's built out of the gauge fields, and I shrink it down to the string scale, it just kind of becomes a D-brane that I can detach and move into the bulk. So I would say here there were two fundamental symmetries. One combination was gauged, and one was broken. Now, in this context, gauge fields on D-branes, you might try to take the story I'm telling you and break it. And one way to do that is let's specialize to D6 branes. So I have gauge fields that come from D6 branes wrapping a 3-cycle. I get a 4D axion from integrating C3 over that cycle. And I can try to just decouple that axion. Say, let me take that gauge field and give it an enormous mass. And I can do that because there's a term in my bulk action that tells me that if I turn on an H3 flux through some cycle beta that intersects the cycle alpha, In my effective theory, this turns into just a theta F4 term. So theta from integrating C3 over alpha, F4 just is D of C3 with all the legs along the 4 dimensions. And this is now an enormous tree-level axion mass. And so effectively, my instanton number symmetry is broken. Instantons can sort of dissolve into F4 flux. And I no longer have an axion in the low energy theory. But interestingly, if I demand that I have chiral fermions charged under these gauge fields on the D6 branes, I can't do this. And the reason is that I get my chiral fermions from intersecting D6 branes, right? So suppose I try to wrap D6 branes on alpha and wrap D6 branes on beta, and at their intersection, I have chiral fermions. Well, now if I try to turn on an H3 flux on beta, I can no longer put D6 branes on beta. One way to think about that is my gauge fields that live on a brane always have the Stuckelberg structure, where they shift under gauge transformations of the bulk B field. But if I try to think about that from the magnetic viewpoint, it means I have this BF kind of coupling, which couples the magnetic dual of my gauge field on the brane to the 3-form flux. And so if I have an integral of this 3-form flux, I have a tadpole. This magnetic gauge field wants to be turned on in 4 dimensions. So there's some obstruction here. If I try to do the simplest thing I can do to get chiral fermions, and then I also try to decouple the axion, there's a clash. I can do one or the other, but I can't do them both at the same time. So I've told you about a few examples. I have some more examples that I've been thinking about, but I don't have time to keep going through a long catalog today. But what I want to emphasize about these examples is there seem to be patterns in them. In cases where I understand the breaking in the instanton number symmetry as being due to monopoles, there are no light electrically charged particles. They all have a mass at the cutoff scale, whether that's the Kaluza-Klein scale or the Planck scale. They're very heavy. If I look at examples that are standard model-like in the sense that they have light chiral matter, I keep finding axions. And I think at least a partial explanation of this comes from thinking about the Kalin-Rubikov effect, which is that when I have light fermions, light electrically charged fermions, and I have a monopole, the boundary conditions for those fermions at the core of the monopole are non-trivial. And at least one way to talk about that effect is that that boundary condition couples the charged fermions to some localized ion mode that lives on the monopole world volume. In the cases where I just saw breaking by monopoles, I could not set up this kind of Kalin-Rubikov scattering process because the charged fermion mass, their Compton radius, is as small as the monopole core size. So it sort of doesn't make sense to ask this question in low energy effective theory in the way that it does in the theories with light chiral matter. So I think there's something deeper going on here where the dion mode and chiral matter are really correlated with each other, and then also correlated with having the symmetry be gauged. Now I had this one example that didn't quite fit the paradigm, the E8 times E8 semi-direct product Z2, where the breaking was not from monopoles, it was something else. That suggests that maybe standard model-like theories don't always require instanton number symmetry to be gauged, but maybe they're broken in a different way than monopoles. For example, maybe you have 2 copies of the standard model, and the sum of their instanton numbers is gauged, but the difference is broken. And that actually connects to some interesting phenomenological models over the years. People have thought about exactly that sort of thing for the strong CP problem, where you have one axion for sort of the standard model and a twin sector, and it changes the phenomenology. So getting toward my conclusions, my working assumption is the current trace F wedge F is either gauged or explicitly broken. In D greater than 4, that is the standard statement that quantum gravity doesn't have global symmetries. In D equals 4, it's a little bit more subtle, but I think there are enough analogies that I believe that it should also be true. If we try to gauge the symmetry in 4 dimensions, we need an axion, or we need something like the massless upquark, and these are classic solutions to the strong CP problem. To me, the interesting question is, what about explicit breaking? Can we either argue that for the standard model, the instanton number symmetry cannot be explicitly broken, in which case we're forced to think about these known solutions? Or can we argue that it can be explicitly broken, in which case maybe there's a different way to think about the strong CP problem if we really understood that? And so again, my working assumption is that when the symmetry is explicitly broken, there should be some sort of defect in the EFT that makes the breaking visible. If that defect is a monopole, well, first, that only applies to cases where the gauge group has a non-trivial fundamental group. And I think it only applies to cases where there are no chiral fermions. I don't have a totally rigorous version of that argument worked out, but I think the Kalman-Rubikov effect is strongly suggestive, and I'm trying to make a more rigorous version of that argument. It could be broken by something like a twist vortex, like the Z2 string in the E8 times E8 case. That only happens when the gauge group is disconnected. And I think I need to characterize that better. I don't feel like I have a general version of that story to tell you. And maybe there's something else. I don't know how to be exhaustive. Maybe there's some other sort of defect that I haven't thought about and haven't found an example of. But I think that if we think about sort of possible topological objects, there should be a finite list of these things that we can think about. And for explicit breaking, I expect theta to be frozen to a discrete set of possible values, and that suggests that maybe some of these theories have new ways of thinking about the strong CP problem, or maybe they reinvigorate some known ideas like the twin axion. So, outlook. What I would like to argue is that either general principles of quantum gravity require that an axion should exist that couples to QCD. That would be very exciting to tell our experimentalist friends who are spending their lives looking for axions. Or we can find some kind of concrete alternative. And I have a story that I think is moderately compelling to me, but needs to be fleshed out more. I need a stronger argument that quantum gravity doesn't allow -1 form U1 symmetries. I'm trying to better characterize the different ways that we can explicitly break the instanton number symmetry, but both by thinking about it in field theory and by looking at string theory examples and trying to see what happens. And string theory gives us, sorry, I didn't mean to do that. Okay, string theory gives us a large set of data, which are known quantum gravity theories. And we can use those. Even if they're not exactly like the real world, we might learn some general principles from them that we can apply to the real world. And the broader context of this is I think axion experiments are making major progress right now. We have a set of experiments, DM radio, ADMX, MadMax, BRED, CAP, which collectively are sort of spanning the whole frequency range where you could imagine discovering an axion. It's going to be another decade or two before they totally exhaust it, but we will, I think, know that answer at some point in the foreseeable future. And it would be great if before they make a discovery or rule it out, we have a better fundamental principle theoretical understanding of what is possible. So thanks.
Yeah, thank you very much, Matt. Are there any questions?
I had a quick question.
Yeah, go ahead.
So maybe I didn't quite follow. I missed some point, but so is the argument that if you have this -1 form symmetry, then you have a defect that on the world volume theory of this defect, you can see explicit breaking effects. But if you have a dionic mode, you can restore that symmetry.
Right.
So
right.
if I don't have an
if
axion,
I just have a monopole, sorry, go ahead. Yeah.
Sorry. So I'm thinking if I just have a monopole with a dion degree of freedom, but I don't have an axion.
Yeah.
Do I end up with a -1 form symmetry, and that's not inconsistent with saying quantum gravity does not like global symmetries?
Sorry, so you said you have a monopole
with a dion,
with the
no
dion,
axion.
but without an axion. Right. So in that case, I would say there is a -1 form symmetry, which is the improved symmetry that knows about the dion mode. And that symmetry had better be gauged because, well, I guess in principle, there could be a different source of breaking of that symmetry, which is something other than the monopole. That's maybe another thing to worry about. But if the only defects you have are things like that admit an improved current, then I would say that improved current must be gauged because that's the only option.
I see. Okay.
I see Greg's hand is up.
Yeah. Can you ask
So
a
Greg,
question?
I saw Greg's hand was up, but I'm not hearing anything from him. It seemed.
Yeah.
I don't know.
Yeah, I did have a question.
Okay.
I was just wondering if you thought about whether the sandwich or quiche picture relating to a topological field theory in 5 dimensions would have give any useful insight about how to think about a -1 form symmetry.
Yeah, I I would expect you have a better answer to that than I do probably. But yeah, I mean, um, I've had some conversations with some of my collaborators about this general thought that we think maybe the right way to define these lower form symmetries is to somehow have auxiliary dimensions in which you can deform things. And certainly I think your picture may be productive for that, but I haven't spent a lot of time thinking about it in detail, and yeah, I would be very happy if someone could tell me the answer to that, or maybe in the future I'll have time to think more about it.
Yes, so I had a comment about it. So maybe it's related to multi-fusion categories or having reducible symmetry boundaries. Because yeah, this is dual to topological local operators, right?
Dual to topological local operators. Well, I think there are cases where, how do I want to say it? If I simply had a three-form gauge field, I guess I would expect to have both the -1 form symmetry and a three-form symmetry. Am I counting right? I would expect to have both the you know, the DC3 symmetry and star DC3. And so I might expect to have that structure there.
So
But for like Yang-Mills theory, we have a -1 form symmetry, but we don't have a corresponding three-form symmetry, right? So the symmetry operators for the -1 form symmetry fill the whole space-time. I don't think there is a corresponding set of point-like topological symmetry operators in Yang-Mills theory.
So what I meant, if I gauge something which is generated by topological local operators, so in 2 dimensions, if I have a 1 form symmetry,
Yeah.
I gauge it, I should get a -1 form symmetry.
No, I agree with, right. So there's settings where they are related. But I don't think 4D gauge theory is such a setting. At least I don't know how to relate the -1 form instanton number symmetry of 4D gauge theory to a story like that with topological local operators.
Okay.
I see Nati's hand is up.
Yeah. Let's assume that your conjecture is wrong.
Okay.
What would go wrong then? For other conjectures, there are various things that would go wrong if the conjecture is wrong.
Yeah, well, I think this is why I said I need a stronger argument, because I don't, if I had a sharp statement of what would go wrong, I would be telling you that.
I would settle for a weak argument.
Yeah, I don't know. I mean, it's all of my arguments are sort of reasoning by analogy, right? This behaves so much like the higher form symmetries that quantum gravity doesn't allow. There's this cobordism statement that
I really disagree with that. There are very few things that are the same as ordinary symmetries. And like when you say symmetry operator, it's not an operator, it's space-time fitting. When you discuss symmetry breaking, it's not like symmetry breaking.
Yeah.
So I would say that all the things, or all the detailed picture is not the same. And that's why I asked, imagine there is such a thing, what would go wrong?
Yeah, I don't
think the arguments that against symmetries that are based on black holes and so forth.
Right.
I don't know if they apply here.
Yeah, I don't know that they do. I mean, like black hole arguments, or the Harlow-Augury argument is sort of specific to 0 form up to, I think, D-2 form, but yeah, I don't have such a thing. So, you know, it's legitimate for you to tell me you're unconvinced, and but I think, you know, there is this phenomenon where when I look at the examples I can find in string theory, it seems they fit the pattern. It seems that they either gauge the symmetry, or that there is some way that I can see that there's a defect whose world volume theory explicitly breaks it, in the sense that it's incompatible with having a gauge field from the low energy EFT point of view. So in that sense, I think there's some sort of circumstantial or empirical evidence for this. But yeah, I would love to have a good argument, and I think at this point it's all analogies and circumstantial evidence. And so if you want to dismiss it, it's dismissible. But I feel like, it seems promising to me and it has a chance of connecting with real experiments. And so I think to me, it's worth some effort from the community to try to think about whether there's a way to make a convincing argument.
So my understanding of these symmetries is that these are not really symmetries. They reflect something about the topology of the parameter space.
Yeah.
And I don't even know what it means in the context of string theory to have a topology of the parameter space. Because, well, we don't have parameters.
Sure.
If you say that the parameter is a field, then we could perhaps discuss it, but then the whole discussion is different.
Well, I think that no parameter statement is actually somewhat related to what I'm saying, right? Because I can tell you, I have a string theory. It contains the low energy effective field theory involves some gauge fields. And if I just know that effective theory, I would say I have a possible parameter of that theory, which is the theta angle. And now we don't believe string theory has such a parameter, so we sort of have some options. And I think the options are there's a modulus that controls it, so it's dynamical, and that's like having the axion in the language I've been using, gauging symmetry. Or there's some principle that selects only certain possible values of theta. There's some discrete set of options. And I think that's essentially what I've been calling explicit breaking. And I guess what I'm saying is that in that case, when there's some principle that selects some discrete set of options, in the cases that I'm familiar with, you can sort of probe that principle using the world volume effective theory of various defects, monopoles, and vortices. So I think at some level that no free parameters in quantum gravity reasoning, which we could certainly make that precise in holography, is very close to what I'm saying. If you like, I probably could have gone back and tried to rephrase the entire talk in that language, and I think the language I was using would have been different, but all the examples and arguments I was giving you would have been very similar.
Thank you.
Thanks.
Are there other questions?
Can I maybe ask one more question? So there's been work in the past on like anomalies of these -1 form symmetries, as phrased here, and we've now seen a couple of examples where they're explicitly broken. Is there a way to understand the explicit breaking, for instance, the lack of a diamond degree of freedom on these monopoles as a sort of anomaly, as having engaged some symmetry which has a mixed anomaly with this -1 form symmetry?
Interesting question. Is there a way to understand these as gauging a symmetry that has a mixed anomaly? I don't immediately see a way to state things in that language, but it's an interesting question. Even if the examples I have given you cannot be stated in that language, it's possible that there are other examples that can be. So that, yeah, it's an interesting question.
Thank you.
Maybe I should also say that when you talk about a mixed anomaly of a -1 form symmetry, in Nati's language, this is what was called an anomaly in the space of coupling constants. So even if we don't use the symmetry language, I think that's clearly a sensible notion.
Yeah, exactly. That's what's got me interested in whether like the lack of a diamond degree of freedom is can like admit a similar description.
Mm-hmm.
Yeah.
Okay, so if there are no other questions, let's thanks Matt again. And can we stop the recording?